Now we're going to look at this example number 2. It says a cylindrical can is to be made to hold 1 liter of oil. Find the dimensions that will minimize the cost of metal to manufacture the can. Okay, now we're dealing with optimization, but now we want to minimize the cost. So make it as small as possible. So to minimize the cost, we want to minimize the amount of materials needed in order to produce a cylindrical can. So we're going to minimize basically the volume or the surface area to try to minimize its size and thus minimize its cost. But we still need to keep, I guess, the same volume though, however. The volume does need to stay at 1 liter no matter what we do. So how do we minimize though the materials to make that happen? So I'll do my best to kind of give y'all sort of a rough estimation of what we're thinking about here. We have a cylindrical can, and it's got a height, and it's got a radius to it for the top and the bottom. So let's give it some letters here. The height will be H, the radius will be R. And we need some formulas to help us out here. The surface area, which encapsulates the container here, is going to be what we really want to minimize to make sure that it costs as little as possible. The formula for that is 2 pi r squared plus 2 pi r h. The volume, V, of this can would be pi h r squared. Now we're going to have to do some slight unit conversions here to kind of get things in order. Since 1 liter is equal to 1,000 cubic centimeters, we need that in volume, we can say that the volume V, 1,000, is equal to pi h r squared. So we have this formula now pretty much set aside for us to use. What I'm going to do here is I'm going to solve this one for h. The goal by solving for h is so that I can substitute for h in the formula for surface area, bringing it down to just one variable from 2. So if I solve this for h, it's going to look like 1,000 over pi r squared. So that's what now I'm going to substitute that, sub into the surface area. Okay, it's going to look a little bit weird, but it'll work. We'll get here A is equal to 2 pi r squared plus 2 pi r times 1,000 over pi r squared. Now some things can reduce a little bit here, which makes it a little nice. The pi will go away. This r will cancel out one of those r's there. So when we're done, we'll have A is equal to 2 pi r squared plus 2,000 over r. And this is now what we want to optimize. We're going to optimize this by using our derivative, basically, and figuring out all that information. So here's how we're going to do this. We need to find the first derivative, a prime. So if we take the first derivative here, we'll have 4 pi r minus 2,000 over r squared. We have to set that equal to 0 and solve for r. To solve for r here, I'm going to multiply through by r squared. That causes that to go away. What I'll have is 0 equals 4 pi r cubed minus 2,000. Now I have to solve for r. Well, let's see, we'll move over the 2,000. We have 4 pi r cubed equals 2,000. So r cubed is equal to 2000 over 4 pi. And we'll have to actually take the cube root of this in order to solve. We'll get r is equal to the cube root of, when reduced, 500 over pi. Awkward type of number, so let's go ahead and get a decimal. 5.42 is what that is approximately equal to. Now, this technically represents the critical number. There's only one critical number here. Now, as far as the size of radius and how big and how small it can get, it's actually, if we made the radius to 0, we can't really make the radius all the way to 0 here, because that would mean that it's no longer a cylinder, it's just a flat piece of metal with no real area or surface area to it. So radius can get close to 0 but never quite all the way, and then you can make the radius just keep getting it bigger and bigger and bigger. For us, we have approximately 5.42 at our disposal, and I just want to know kind of what's going on with this. Now, if I choose numbers like 5 and 6 around next to it, just to check what's happening with the derivative, and if I plug in 5 to the derivative, it turns into approximately negative 17.2, and if I plug in 6 to the derivative, it comes out to be approximately 20. What that means is the derivative is positive and it's increasing there, and it's negative and it's decreasing here, meaning that at this number that we found for the critical value, that's the lowest it's ever going to get. That's both the absolute and a local minimum. So we don't really have to check much else, and we really don't really have to check this very often. I'm just kind of showing it to illustrate the fact that we can know for sure that 5.42 thereabouts is indeed the absolute minimum for this particular situation. So the answer then for minimum surface area and thus cost, we use R is approximately 5.42, okay, and then H, we have a formula up above for H. We had solved for that. It was 1000 over pi r squared, so that would be approximately 1000 over pi 5.42 squared. It's approximately 10.84. Now I should put units. Those will both be measured in centimeters.